All right, our topic for this morning is line integrals. So a line integral is a new type of integral that is similar in some of the large scale features to the path integrals or arc length integrals that we talked about recently, but they're instead measuring the interaction of an object with some vector field that it's moving through. And what a line integral does is it tells you about transfer of energy. If you're moving through some kind of field that exerts force on you, no matter where you are, the force can either help you by pushing you in the same direction as you're moving, or it can hinder you by pushing in the opposite direction. And so what a line integral does is it takes all those and it totals them up. And from a kind of physics point of view, it's measuring a concept called work. Work is unfortunately one of the most difficult things to explain because its name doesn't actually measure how we think about work as human beings, but that's what's going on. Is either the line integral helps you or hinders you, it gives you energy, or it takes energy away from you. And the line integral gives you that total contribution. So here are some examples. Here on the left, we've got an object moving through a vector field. In this case, the vector field is moving in the same direction as measured by all of these green arrows. And so when the object moves through it, we get a positive contribution. It gives us a total net gain in energy. Whereas in the upper right, we get a total contribution because the vector field is pointing in the opposite direction. We get a negative contribution. We lose energy. Whereas down at the bottom, the vector field is kind of moving perpendicular to the object that's going through it. And here, we can imagine that the total contribution to our energy is zero. We neither gain nor lose. So there's a combination of two factors. One of them is what direction we're moving, and the other is what direction the vector field is pointing. And in general, it's a little bit more subtle than that. When we're moving through a vector field, we have an angle that's made between our direction vector, the velocity vector, and the direction that the vector field is pointing. So what we want to do is we want to kind of say, well, the part that's moving in the same direction as us or in the opposite direction can give us energy or take energy away, but the part that's pointing perpendicular is going to do nothing. It doesn't kind of exert energy or give energy or take any energy away. So to calculate the total contribution, what we need to do is we need to kind of figure out what part of the energy transfer is happening by projecting it down and calculating only with that. So there are a couple things about this that make it really kind of fundamentally different from the path integrals, the things like arc length or measuring mass of curves. With line integrals, direction matters. So when you are moving in one direction or moving in the opposite direction, one direction may be giving you energy and the other direction may be taking it away, because in one direction you're moving with the field, in the other direction you're moving in the opposite. So if you switch the direction of the curve, the integral switches sign from positive to negative. So it's very important in this case to keep track of what's called the orientation. It's just the direction, which direction, which part of the curve we start at and which part of the curve we're moving to. So it doesn't matter which parameterization we use so long as it goes the correct direction when we're calculating a line integral. So if we got one curve, we can parameterize it in multiple ways, but all of them are going to give us the same answer when we calculate the total energy transfer. As an alternative, a different way to think about this physically is to instead imagine that the vector field, instead of like an energy field or something like that, or a force field, that the vector field is measuring flow of a fluid, the total rate of movement of a fluid. For some kind of curve that's moving through it, we can imagine that this fluid flow is trying to push stuff that's on the curve from one side to the other. And then the physical concept is sometimes called circulation in that case. And still, we're only measuring flow in the same direction as the path, rather than the opposite direction. So here, if we have a vector field that's kind of pointing around this direction, we said that it was rotating counterclockwise. One way to talk about that is to say, hey, let's imagine we're moving in this vector field along this curve. When we move around that curve, the total fluid flow is going to be counterclockwise, and we can measure the exact amount of circulation by calculating this line integral.